Hello everybody, this is Dan Bigman. I am your GPR professor from LearnGPR.com and president of Bigman Geophysical, a full-service geophysics firm. We work with archaeologists and environmental professionals. We work with structural and civil engineers on utility locate work and concrete scanning and testing. We work with geologists and geotechnical folks to characterize subsurface problems such as sinkholes and voids. And in today's video, we're going to talk about bridge deck inspections with ground penetrating radar. It's an application that we've been doing a lot of lately, and there's some, I would say confusion, but maybe misunderstandings about what it can do, what it can't do. And so what we'll go through today is some of the problems in the US for bridges, we'll go into some of the defects. So we'll talk about stats first, then we'll talk about some of the defects that are occurring on the bridges. And then finally, we'll talk about GPR and how it can be applied to identifying kind of the ingredients of corrosion, corrosion itself, of reinforcement, and then the potential results of that problem. So start out with some statistics. So in the American Road and Transportation Association's 2024 report, they came out with a series of stats on the problems in bridge decks in the US. So first they found 221,800 spans of bridges need repair. Okay, need repair. Spans need repair. That is 1 in 3 bridges in the US are in need of some sort of repair. So, second, they found 76,175 bridges in the US need to be replaced. That's about 1 in 9. That's about 1 in 9 bridges. Finally, they found that 42,067 bridges in the US are what they consider to be structurally deficient. This is the major issue of what's going on. And so just because a bridge needs to be replaced doesn't mean it's structurally deficient, but that's about just under 1/10 of the bridges in the US are considered to be structurally deficient. So this is all of an issue, and is the problem getting better? The answer is yes, it is getting better. So from 2023 to 2024, 0.8% of bridges improved. So that's a good trend. We'd rather it get better, but it's still way too low. So less than 1% of the bridges from 2023 to 2024 got reduced as no longer structurally deficient. So characterizing all this, this is a real big issue in the US. So what are the potential problems that bridges face that require them to either need repair, replacement, or are defined as structurally deficient? There's 2 main categories of defect. Okay, there's 2 main categories of defect. So the first is mechanical, and the second is chemical. Now, there's a long list of each of these, but I'll kind of give you 2 of each. So for mechanical, one of the examples or common is freeze and thaw effects. So you get expansion and reduction of steel inside of the concrete, in concrete bridge decks, and that can create problems like delamination, cracking, and other things. Another problem is abrasion. And so this basically, is from wear and tear at the surface, creating rough surfaces, pitting, and can be problematic, right? Also, that's considered erosion and starts to get down into the concrete bridge deck. So for example, reinforcements that might be embedded at sufficient depth may no longer be embedded at a sufficient depth. So these are 2 common mechanical problems. Chemical problems include alkali silica issues, And this basically is a chemical reaction that creates cracking at the surface. Almost looks like a braid of rivers, if you've seen that. And sometimes there'll even be an ooze, like a gel that oozes out of those cracks. This is a problem, pretty common. And then finally, and the focus of the video today, is corrosion. This is an issue when basically chlorides infiltrate the concrete, interact with the steel reinforcements, and create an oxidation process which expands the steel, reduces the steel but expands the space and can cause cracking and structural problems within there. And so this is the one that we're going to focus on today when we talk about GPR. So really what I want to do is talk about what are the ingredients of corrosion, right? What does corrosion look like itself, and what are sort of the repercussions of it, and what are the expectations from ground penetrating radar in trying to identify these problems within concrete bridge decks. So we'll go through a few things. Two ingredients, right, that sort of cause corrosion that are identifiable by GPR. So not all the ingredients can't necessarily identify the chlorides and things like that with GPR, but there's two kind of conditions that make concrete bridge decks more susceptible to corrosion, and these two can be identified by ground penetrating radar. And so the two ingredients are shallow cover and moisture. Okay, so shallow cover and moisture are two of the things that are, that are kind of preconditions to creating, not necessarily, but are two common ones that create corrosion in concrete bridge decks. So shallow cover, what are we expecting then to see in the ground penetrating radar when we have shallow cover? And what is shallow cover? Shallow cover is basically, here's your concrete bridge deck, and it's 1 inch down, 2 inches down, 3 inches down, down to 10 inches down or whatever the case is. And you have reinforcements that happen to only be, an inch or so below surface. And this makes them more susceptible to intrusions from the surface, such as moisture or infiltrating chlorides. That's what shallow cover is. So what are we looking for then in GPR when we're trying to identify reinforcements that are buried too shallow in the concrete? Two things. Number one is obviously depth conversions within the ground penetrating radar. This can only be used if you're doing velocity estimates to make accurate depth estimates. And so that's one. And then, so depth is one. And second is two-way travel times, assuming that you have consistent velocities. So, for example, if you have similar two-way travel times and your velocity is consistent across your bridge deck, then that would be an indication that you might be identifying shallow reinforcement. So you're looking for shallow or short two-way travel time areas to indicate shallow reinforcement. So, for example, you might have a couple that are shallow and then some that are buried deeper, right? This would be a shorter two-way travel time compared to this. So that's what we're looking for to identify shallow cover. We had an example recently that we did on a project where it was a new build and they were unsure if the concrete cover was the same and consistent across the entire bridge or if it varied. And what we found was the velocities were consistent across the bridge, but the two-way travel times were longer towards the outside of the bridge, shorter towards the inside, suggesting that the interior center of the bridge was more susceptible to potential corrosion in the future. And this was a bridge that hadn't even been used yet. And so we were doing quality verifications post-construction for this company. Okay, second is moisture. And so moisture is another major ingredient. And I'll talk in a second about the difficulties to differentiate between moisture and active corrosion. Because sometimes there's an overlap between the effects that the GPR will record for each of those. So it may be susceptible, it may have the ingredients, but it may not be corroded yet. Doesn't mean it's not a coming problem. So moisture is number two. And moisture also has two things you can look for. First of all, you can look for slowing down of GPR waves. That's number one. So for example, if you have consistent depths of your reinforcements, and you find that you have fast velocity here, you have a slower velocity, and then fast velocity here, this may suggest that this area is particularly susceptible to future corrosion, if not already corroded. Why is that? Moisture in concrete reduces the GPR's velocity in the concrete. And so typical concrete might be, between, your dielectric permittivities might be between, 4 to 6 or 7 for healthy concrete, but then they might get up to things like, 9 to, could be anything. Could be, we've seen some that are extremely moist, wet and waterlogged up to 15. So there's a wide range, but, lower permittivity values indicate faster velocities, indicate healthy concrete. Higher permittivity values indicate slowing down, indicate more moisture, and the potential susceptibility for future corrosion. The second thing that you can find, to help indicate that there's additional moisture in the concrete is going to be reduced amplitudes. Reduced reflection amplitudes. So what does that mean? If there's more moisture in a specific part of the bridge deck, the active moisture mixing with the concrete material will actually deplete the GPR signal faster. And so by the time you get to the depth of the reinforcements, you're just working with less energy in areas that have moisture in them as compared to areas that don't have additional moisture and are healthier. And so you might get very strong responses in areas that are healthy, and then you might get just really subtle responses in areas that are infected because you have less energy that is even capable of reflecting off the reinforcements by the time you get down to them, because the moisture has already depleted some of that signal, differentially more than in areas that are healthy. So those would be two potential indicators for moisture in concrete bridge decks that may indicate an area that is either actively corroding or is susceptible to corrosion. Okay, so what about corrosion itself? So corrosion itself has a few indicators as well. One is going to be reduced amplitudes. Reduced amplitudes as well, and this is where sometimes it's hard to differentiate between areas that are corroded or just have additional moisture or have additional moisture and have already been corroded. And so with why do you get reduced amplitudes? Well, so the main reason you get reduced amplitudes for corrosion without the existence of additional moisture, redefine our bridge deck, is that if you have a reinforcement, of a given size, and then you have, it's not even close to being the same size, and then you have another one that's corroded, but of the same size when it was embedded, what happens is, through the oxidation process, you actually get reduction in the size of the steel. And so it becomes smaller, and then it becomes surrounded, right, with the corroded area. So overall, it may be similar in size, or actually may expand. That's pretty typical. And so now you have less overall steel on the corroded out reinforcement compared to the non-corroded reinforcement. So surface area plays a role in how much energy comes back to the GPR at the surface. So if a GPR is at the surface and it's putting out a signal, then more of this energy is going to come back because you have greater surface area. And on the infected steel that's now oxidized and corroded, you have less steel in total. And so as it comes down, right, just a little less energy is coming back to the surface compared to the healthy example, the non-corroded example. And so because of that reduction in steel, expansion of oxidation and corrosion, you will potentially see reduced amplitudes. Now, how can you tell if it's actually reduced amplitude from corrosion or reduced amplitude from additional moisture inside of the concrete? Well, the main way to do that is checking the velocities across your bridge deck. So instead of doing one velocity estimate at one location, you do many velocity estimates and verify that the wave is moving at the same speed here as it is here. If the wave's moving at the same speed in the healthy area, right, or the non-corroded, and it's moving at the same speed here, then we can, it indicates that similar speeds, the reduction in amplitude is not due to moisture, it's similar moisture, reduction in amplitude is likely due to corrosion, assuming that they're at the same approximate depth. So checking velocities, often you're going to do this through hyperbola fitting or matching, which is a common way to estimate velocities. Similar velocities suggest excuse me, that the reduction in amplitude is due from corrosion. If you have changes in velocity, because this area happens to be more moist and you have more water in there, it actually will be difficult to tell if active corrosion is occurring, because you would be expecting that at least at a minimum, the water is going to be reducing the amplitude of the response. And so it may or may not be corroded, and you're still going to get that reduction in amplitude. So it's hard to tell exactly what's going on, but that's sort of the main use of this method to check whether or not there is corrosion going on. And that's what we often do across large scales of bridge decks, where we're evaluating a full bridge deck, whether it's somebody who's on site and the bridge is closed down. We have systems that can be actively used by a single individual. We also have systems now which have developed, and this is an important kind of development, which are vehicle mounted. They don't slow down traffic, and you're able to cover in a very high resolution the distribution of reinforcements inside of the concrete bridge deck, and then evaluate afterwards, where are the waves slowing down, where are the amplitudes different, and so forth. Okay, what are the concrete cover of those reinforcements, and are there areas that are particularly susceptible? So we're able to do that now. And one final piece then is going to be delamination. So this is really the response to the corrosion of the concrete, right, will be cracking or delamination as one example. And so here, what are we looking for? How does that occur? Well, as the steel reduces and the corrosion expands, it puts pressure, outward pressure on the concrete, and it can cause delamination inside of the concrete, which is a crack that's somewhat parallel to the surface. It doesn't have to be exactly parallel, but the laminations are not seen at the surface. They're masked because they're interior to the concrete. This is what creates the severe structural deficiencies in many of these situations. So how does GPR identify this specifically? Well, usually you're not looking then for hyperbolic reflection geometries, which is typical for reinforcements because they're cylindrical objects. We're looking for horizontal responses that are somewhat parallel to the surface. Again, they might kind of do this, or this, but they're interior and they're somewhat parallel to the surface. So first is you're looking for a different geometry as far as the response goes. Right? Horizontal or planar is another word we use. Responses. And then the second indicator that it's a delamination is going to be a phase shift. And so this is because a phase shift as compared to the steel, because going from concrete to steel, you have an increase in dielectric permittivity, or an effective decrease in velocity. But going from concrete to air, which would be the crack, would be a decrease in dielectric permittivity and an increase in velocity. And so when that happens, the actual color sequence that's returning, the wave that's returning back, and you're plotting it, right, is going to be different. It's going to be shifted for a delamination as compared to a steel reinforcement, okay? And so for something like this, you might see we'll call it blue, black, blue, right, for this steel, okay? Here you'll also have a blue, black, blue, but it will be less dramatic because it's corroded, right, compared to here. And then here you would actually have a black, blue, black, indicating an actual, different response by the wave when it hits the delamination compared to when it hits the steel. So that's kind of a representation of what you would expect in a situation like this. I hope this was helpful. I hope this cleared up some confusion that you may have had. I hope this has, helped you go make better interpretations. If you have a bridge deck that needs inspecting, if you're an engineer and you're working with a DOT, if you're a municipality that owns some bridges, or if you're just looking for additional help, or you want to get trained on how to do this properly, we can help you. Go to LearnGPR.com and sign up for classes, or go to BigmanGeo.com. Both of those are up here, and fill out the form, and one of our people will get back to you. Thank you so much. I appreciate it. Stay safe out there, and good luck.